Thank you. So hi, I'm Jianxin from Intel. What I'm going to present today is our work on using DMA-BUF as a mechanism to support GPU memory in RDMA operations. Next slide. Yeah, I'm going to start with an overview of the RDMA operation itself, and especially when combined with the GPU memory. Next slide. Okay, in a nutshell, RDMA is a DMA plus network. For example, if we have a RDMA write operation, is basically in the initiator side, there is a DMA read. The NIC is going to read the data from the buffer and then send the packet over the network. And at the target side, there is our DMA write. For RDMA read operation, just the same, but with the direction reversed. The initiator will do a DMA write, and the target will do DMA read. On the picture on the right-hand side, we can see that the datagram. We can see the flowchart of this operation. So the NIC is doing the DMA from the system memory to the NIC's packet buffer. So in order to do this operation, the NIC need to get this DMA address for the buffer. So this is usually done in advance with a process called memory registration. So the NIC driver will provide all the information needed to do the address translation to provided the DMA address as a list to the NIC. The NIC will save those things internally into something like a memory translation table. So in order to set up the DMA operation, so the memory pages need to be pinned. So when the DMA is in progress, the memory doesn't, the physical memory doesn't go to, being accessed to use a different purpose. So for the DMA operation, it needs to use the boss address, not using the virtual address. This is usually done at time of memory registration. For example, for the user space buffer that located in the system memory, the memory pinning is usually done by the function called getUserPages. And also to get the DMA address, the kernel function DMA-MAP-SG and a family, there's many similar functions. Those are used to translate the virtual address, not the virtual address, translate the page structure into the boss address. Next slide. So in order to use the GPU memory in the RDMA operation, so something needs to be done a little bit differently. So one reason is that because the GPU memory is local, the NIC driver cannot directly pin the GPU memory, and it doesn't know the DMA address of the GPU memory. So you cannot directly call this get user page or the DMA map SG kind of function to do the translation. Instead, the DMA driver, the NIC driver and the GPU driver has to be work closely to do some information exchange. The picture at the right-hand side shows the concept of how this is done. So basically, the GPU driver has control over the GPU and the GPU memory. So it has to provide some mechanism to get the information of the GPU memory to the NIC driver. So there's a handshake there. So the information is changed. The NIC driver at the memory registration time, when it gets the information from the GPU driver, it will finally deliver the DMA address to the NIC, and the NIC can use those information to do a DMA transaction with the GPU memory. So this DMA transaction is because both the NIC and the GPU they appears as the peer on the PCIe network. So this is a peer-to-peer DMA. Is different from when you are using the system memory. One example of supporting this kind of operation is the peer direct from Mellanox. The peer direct basically provide a plug-in interface for the kernel RDMA driver. Each GPU driver will provide a plug-in module that will implement a certain set of API functions that will be called by the RDMA core. When the RDMA core is doing the memory registration, it will invoke the plugin functions one by one to ask if the memory is owned by that specific GPU, and the GPU plugin will, when it detects the memory is owned by itself, it will respond, and later and associate itself with that memory, and the RDMA core will then using the CPU specific function to pin the memory and to do the address translation. So this has been worked fine for so many years, but the only issue is this is not in the upstream. It's only available in the Mellanox version of the OFA. So what we want to do is to see if we can have an upstream solution to achieve similar result, but not. So our proposal is to use the DMA-BUF as the mechanism to do the information exchange. Next slide. So here I will give a brief introduction of what is the DMA-BUF and how it works. Next slide. DMA-BUF is a standard mechanism in the Linux kernel. The purpose is for sharing buffer between different device drivers. In the concept of a DMA-BUF, the buffer is located by one driver, and that one is called the exporter. The exporter will export the buffer as an object called the DMA-BUF object. At the time of exporting, it has to define a set of operations. That set of operations will done all the necessary things to pin the buffer or to do the address translation. After this exporting, it can also associate the buffer with a file descriptor. The file descriptor then can be delivered to the user space and then send back to the other side, to another driver that want to use the buffer. So that part is called the importer. The importer will translate the file descriptor into the DMA-BUF object again, and then it can attach itself to the DMA-BUF and do and call the mapping method to do the address translation. So after the mapping, the importer has the information about the physical address, or the DMA address of the buffer, and then it can use that address to do the peer-to-peer DMA transaction with the memory located in the other side. Next slide. Here is the overview of the API of the DMA-BUF at the exporter side. So basically, there are two functions. One is DMA-BUF export. The other is DMA-BUF FD. DMA-BUF export is the main function to export the BUF as a DMA-BUF object. By calling this, it has to define a set of operations. Many of them are optional, but several are mandatory. Mainly, there's one called the map DMA-BUF. That one is doing the address translation. It's similar to what DMA map SG does. And it also, at the same time, it should also pin the buffer. And there's a corresponding map function. And there's another function to release the DMA-BUF. And those functions are called by the import side DMA-BUF API to achieve various functionality. And the DMA-BUF FD function is used to associate the DMA-BUF object with a file descriptor. Next slides. So at the importer side, there's also a set of functions. The most importantly, there is a DMA-BUF get to retrieve the DMA-BUF object from the file descriptor, and there is a DMA-BUF attach that is to associate the device, the at the importer side, to the DMA-BUF. So the DMA-BUF, because the attachment function is actually calling the method exported by the exporter, so that the exporter at this time has the opportunity to checking if the storage back in the DMA-BUF is actually accessible to this device, and so it can return success or or failure, depending on the situation. And also there's a optional to be attached dynamically. So that is for a different scenario. And the other important function is the DMA-BUF map attachment. This is the function to do the address translation. At this time, the exporter will determine if where the buffer is located, and need to pin the pages and get a DMA address list. Next slide, please. Now we'll show our implementation of how to use the DMA-BUF to support the GPU memory RDMA. Next slide, please. So the implementation is mostly focusing on the memory registration side, because that's where the GPU memory is different from the system memory. Here is the flow chart of the entire path to do the memory registration. So it started with the memory allocation. The memory allocation is done by the GPU driver. When the GPU driver do the memory allocation, it will call the DMA-BUF export function to export this as a DMA-BUF object. From the user space, this is achieved through the DRM interface. The user space library calling into the GPU driver to do the memory allocation. In return, it will get the address, size, plus the file descriptor. An application will, at the right-hand side, the application will go into the various user space library to do the memory registration. Along the path, the file descriptor will need to be passed down together with other parameters. And all those parameters finally go into the kernel RDMA driver. The kernel RDMA driver will then import the DMA-BUF object and call the DMA-BUF API functions to set up the DMA address for the GPU memory. The NIC, when doing the RDMA operations, will then use those information to perform peer-to-peer DMA transaction over the PCI Express bus. Next slide, please. So to do this, we have to make changes at several layers of software stack. From the GPU software side, the DMA-BUF is already supported by many existing GPU drivers. Mostly they are as a part of the DRM, germ, and prime interface. They are accessed by the I/O control method through a special device. But currently, the GPU drivers, together with the DMA-BUF implementations, they may not be optimized for peer-to-peer access yet. So there are some improvement ongoing on that side. For the user space library, it has to be provide interface to get a DMA-BUF file descriptor. So it should be have as a property of the memory being allocated. For example, it can be as the IPC handle. So applications is going to use that user space library to do the memory allocation. So this is not a general malloc, and the user space library also don't want to call the I/O control directly. Next slide, please. From the importer side, the RDMA driver needs to support the DMA-BUF as a user memory using a specialized IBU memory get functions. So basically, in the memory registration path, IBU memory get is called to pin the pages and get the get a list of a DMA address. For the DMA-BUF, we need to use a specialized version. That version has additional parameter to pass in the DMA-BUF file descriptor down to get all the information needed. The user space verbs, we need to define two new commands to register the memory that is associated with a file descriptor. So one command for the regular registration, the other for the re-registration. Also, these two commands has the two additional parameters to pass the file descriptor down. Next slide. So in order to actually do the memory registration, the device interface has also to be changed to add two methods, so the memory registration can be done with the actual parameter. The vendor drivers need to implement these two methods for the device driver. So this is optional, only if the vendor driver want to support the DMA-BUF, and it can choose only to support one, not the two. Only support the regular registration, not the re-registration. And you just need to set the command mask accordingly. The next slide, please. In addition to the RDMA driver in the kernel, the user space RDMA library also need to be changed to accommodate this new feature. Similarly, new functions is introduced with actual parameter to pass the file descriptor down. Next slide, please. The user space also need to add the uverbs commands function, so the information can be passed down to the kernel. And the user space also has a similar vendor-specific device structure. So in this, we need to add these new functions. So the vendor-specific operations can support this new file descriptor-based memory region. Next slide, please. So another layer of the user space stack is the OFI. So in order to support the file descriptor-based memory region, the OFI need to use the FI-MR reach attribute, the function to register the memory, because this memory registration attribute has actual fields for the heterogeneous memory, including the GPU memory. In this here, we have this interface parameter that used to distinguish between different type of memory allocation. This could include the other GPU APIs, but for here, DMA-BUF is going to be a separate interface. And for this separate interface, we have actual parameter file descriptor here through the device field. And the provider need to support this, to recognize this field, and need to handle the registration properly. So if the provider have this support, it is indicated this by a special capability bit as FI-HMAN. Next slide, please. So right now, we have already implemented a software prototype to support this, all the things discussed previously. So this is based on upstream Linux kernel 5.6 and the most recent user space RDMA core library. And we use Intel GPUs that use the i9-15 driver. We use the Manox Connect64 EDR NIC as the RDMA NIC using the upstream driver. So we add all the necessary things about the DMA-BUF to the RDMA driver. And this has been tested working fine, and we achieved the expected performance. The next step is to getting the code changes to upstream. So we have sent the first set of patches to the Linux RDMA list and got reviewed and got many feedbacks. So we are working on revised patches, and we are also working on the GPU driver development and the DMA-BUF infrastructure development. So we can have all the pieces needed in the upstream. And also we want to get this upstream of the user space library in the RDMA core and the OFA changes. I think that's all I have today. So I'm open for questions now.
Any questions? Okay, so I know how to find Jianxin if in case, hold on, there is a question coming in. The question is this being proposed in Linux?
Yeah, this is for Linux.
Hey, Tom, if you want, I can open the mic. Hold on just a second. All right, there you go. Give it a try. Okay. Yep, I guess that answers the question.
Thank you. Can you hear me?
Yes, I can hear you, Tom.
Oh, okay. Thanks. My question was more, has it been submitted as a proposal in Linux? Not that it is directed toward Linux. That's obvious.
Okay, yeah. So, you know, the Linux, we have submitted to the Linux RDMA list because Linux has many subsystems. So this is part of the Linux RDMA subsystem. So we submitted the RFC patches. So it's not the formal submission yet. So we just it's for request for commands. So yeah, so it's not official yet.
Okay, because I'm aware of similar efforts going on in other directions that don't necessarily depend on the DMA-BUF, or maybe I'm mistaken.
Yeah, there are many similar things. I mean, there was even effect related to DMA-BUF before, but it's different. Yeah, I saw it also.
Okay, so it's an alternative proposal. Okay, thank you.
Thank you.
Okay. All right, so we have 15 minutes of break time. Thank you, Jianxin. Let's meet again at 10 a.m.
Thank you.